Okay, hello everyone, welcome back to EduQs. So today we are going to continue with our module 1. Under module 1, we are going to see the atomic structure, that's chapter 3. The atomic structure comprises of the various lessons. We have the atomic but subatomic particles, we have radioactivity, quantum numbers, the electronic configuration, the SPZF configuration. We go straight to lesson 1. Lesson 1, subatomic particle or the atom. Atom. The atom is the smallest particle of matter that can take part in a chemical reaction. The atom is made up of subatomic particles. The subatomic particle includes the protons, the neutrons, and the electrons. The protons are positively charged. The neutrons have a charge of 0. The electrons are negatively charged. So these subatomic particles were discovered by scientists through experiments. So the table below summarizes the history of subatomic particles and their discoveries. Table. Subatomic particle. Location. Charge. Discovery. Here we have the proton. The protons. The protons is found in the nucleus. The charge is +1. Discovered by the Rutherford gold fuel experiment. The Rutherford gold fuel experiment. The Rutherford gold fuel experiment. So we have the neutrons. The neutrons still found in the nucleus. The charge +1. The charge 0 is neutral. Then discovered by Chadwick. So Chadwick, beryllium fuel experiment. Lastly, we have the electrons. So electrons. Location, find the shells or orbitals. The shell or orbitals. The charge is -1. Discovered by J.J. Thomson. J.J. Thomson. Cathode ray experiment. Cathode ray experiment. So that's a brief history of the discovery of subatomic particles. So we have the protons, find the nucleus, the charge is +1. The Rutherford gold fuel experiment. The neutrons, still find the nucleus, the charge is 0. The Chadwick beryllium fuel experiment. We have electrons, find the shells or orbitals, charge is -1. The GC Thomson experiment. The atom is electrically neutral, meaning the charge of an atom is 0. Why? We have equal number of protons and neutrons. So the proton and neutrons counterbalance each other. At the end of the day, the charge is 0. Such that the charge of the proton is +1. The charge of an electron is -1. At the end of the day, we have 0. So an atom is electrically neutral. So from the Niels Bohr proposition of an atom, according to Niels Bohr, an atom can be denoted as follows. We have the nucleus. In the nucleus, you have protons, protons plus neutrons. Then the electrons are found in the shells. So the electrons are found in the shells rotating around the nucleus. So this is the Bohr model of the atom, which was different from the G.G. Thomson model. So these orbitals, they are called energy levels. So an atom can occupy a fixed energy level. That is why we say an electron in an atom is quantized. So here the first energy level has 2 electrons, the second has 8. 1, 2, 3, 4, 5, 6, 7, 8. And so on and so forth. So in a nutshell, that is the atomic structure and their various discoveries. So let's now go to the representation of an atom. So how can we represent an atom? Representation of an atom. An atom is represented as X. So let's say you have an atom X. X. AZ. Where A is the mass number and Z the atomic number. The mass number is simply the sum of proton plus neutrons. So A is the proton plus the neutrons. Then Z is the proton number. So let's do the mathematical operation A minus Z. So we're going to have A minus Z is equals to, we have P plus N minus P. Open the brackets such that we're having P plus N minus P. P cancel. We're left with A minus Z is equals to N. It simply means that to have the neutron number is the mass number minus the atomic number for the mathematical operation that I've just completed. So let's take a typical example. So let's take the atom of aluminium. Example. Aluminium 1327. In this case, what does 13 and 27 represent? 13 represents the atomic number. The atomic number or the proton number or the proton number or the electron number. Electron number. 27 represents the mass number. And here, we can be asked to calculate the proton, the neutron number. We use our formula. A in this case is 27. Z in this case is 18. But we know A minus Z is equals to N. It means 27 minus 13 equals to N. So 27 minus 13 is 14. So having 14 is equals to N. It simply means that the atom of aluminium has 14 neutrons. This folds only if and only if the atom is neutral. If the atom is charged, this one will not hold again. The proton number will no more be equal to the electron number. So let's see a case where the atom is charged. So if you have an atom that is like positively charged, let's take the case of magnesium. Magnesium 2 plus 12, 24. In this case, the proton number is not affected. The proton number is still 12. So the proton number is 12. But the electron number is affected such that because if the atom is positively charged, it means it has lost electrons. In this case, it is plus 2, meaning that it has lost 2 electrons. Normally, the number of electrons was 12. minus 2 electrons, the number of electrons dropped to 10. But the neutron numbers are not changed. A minus Z is equals to N, such that 24 minus 12 equals N. So N is 12 neutrons. We clearly see that if the atom is positively charged, the number of electrons drop. If the atom is negatively charged, the number of electrons increase. Let's consider the ion of sulfur 2 minus 1632. The proton is still 16, but the number of electrons here will differ. Why? Because the atom is charged. The charge of the ion is 2 minus. Now we have sulfur 2 minus, meaning that sulfur has gained 2 electrons. So, what's the physical significance of that? The number of electrons is now 16 plus 2, which is 18. But the neutron number does not change. The neutron number is still A minus Z is equals to N, such that 32 minus 16 is still N. So 16 equals to N. In this case, we have 16 N's. That means the number of neutrons change. In conclusion, what can we say? We can say that, okay, if the atom is charged positively, it has lost electrons. If the atom is charged negatively, it has gained electrons. Okay, what you have to remark, take like a remark for a neutral atom, the electron number is equals to the proton number, which is the same as the atomic number. That's if the atom is neutral. So if the atom is charged, the electron number is not equals to the proton number. Meaning, the number of electrons can either increase if the atom is negatively charged or decrease if the atom is positively charged. So we're going to see the notion of isotopy, because there are some atoms of the same element that have the same atomic number but different mass number. We'll go to the notion of isotopy. 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 So I'll be obliged to write the definition of isotopy down because I'll make use of it. So isotopy is the existence of atoms of the same element having the same atomic number but different mass number due to a difference in the neutron number. So I can read the definition for us. Isotopy is the existence of atoms of the same element having the same atomic number but different mass number due to a difference in the neutron number. So from the definition, we can have two cases. We can have the case of, let's take an example. So example, let's take the case of carbon. I have carbon 14, 6, and carbon 12, 6. What is the similarity between these two atoms? The first similarity is at the level of the proton number. We see the proton number are the same. The same number of protons, which is 6. But what differs? Let's calculate, because we said the difference in neutron number. So let's calculate the neutron numbers. So the neutron number will be 14 minus 6 is 8. Here is 12 minus 6, 86. We clearly see that the neutron number are different, even though they are atoms of the same element. The element here is carbon. So we can calculate the RAM, the relative atomic mass of, if and only if there exist different isotopes. So if there are different isotopes, we can calculate the RAM. So we're going to give a formula. So the RAM is equals to percentage of X times mass of X plus percentage of Y times mass of Y divided by 100. Divided by 100 if and only if X and Y are given in percentages. So let's take a typical example. Typical example. Calculate the relative atomic mass of chlorine, given that 75% chlorine 35 and 35% chlorine 37 exists. In this case, we have been given two isotopes. We have the isotope of chlorine, that's chlorine 35. We have also the isotope of chlorine 37. We have been asked to calculate the relative atomic mass. We can use a formula. So the RAM is equals to the percentage for chlorine 35 is 75% times the mass. The mass is 35 plus the percentage of this guy is 25 times the mass, it's 7, divided by the sum of percentages, which is 100. In this case, we are going to have RAM equals to 35.5. You punch your calculator such that you have 75 times 35 plus 25 times 37 all over 100. So the answer is equals to 35.5 for chlorine 35. In this case, we are going to take a more complex exercise. This one is like ordinary level, just introduction. Advanced exercise now, but the methodology is the same. So let's take a small exercise. Calculate the relative atomic mass of iron. So they gave us a table. They gave us a graph. Graph. So here we have iron. So here you have the mass to charge ratio. Abundances. Here we have iron 50, 54, 55, 56, 57, 0.1, 0.6, 0.3, 0.1. We have been asked to calculate the relative atomic mass of iron 56.